Before we dive into one of the most remarkable engineering solutions of World War II, hit that like button and subscribe to the channel. Leave a comment below and tell us where you're watching from, whether you're a history buff in Texas, a tank enthusiast in Germany, or just discovering this incredible story from anywhere else in the world. October 23, 1942. El Alamein, Egypt. British tank crews watched in horror as their new American-made Sherman tanks brewed up, burst into flames, within seconds of being penetrated by German anti-tank rounds. The crews called them Ronsons, after the cigarette lighter advertised to light first time, every time. Polish tankers had an even grimmer name, Tommy Cookers. But 2 years later, in the hedgerows of Normandy and the forests of the Ardennes, German gunners were experiencing something they couldn't explain. Their perfectly aimed shots were penetrating Sherman armor, but the tanks weren't burning. The five-man crews were escaping. The tanks were being repaired and sent back into battle. What had changed? The answer would be written in water, physics, and American ingenuity. The story of the Sherman tank's wet ammunition storage system represents one of the most critical engineering innovations of World War II, yet it remains largely unknown outside military history circles. This wasn't about making a more powerful gun or thicker armor. This was about solving a fundamental problem that was killing Allied tank crews at an alarming rate. Between 1942 and early 1944, studies revealed a devastating statistic. 60 to 80% of Sherman tanks that suffered armor penetration caught fire. Given that the M4 Sherman was the backbone of Allied armored forces, with over 49,000 produced during the war, this represented a crisis of catastrophic proportions. Every Sherman sent to the front lines was, statistically speaking, a potential crematorium for its five-man crew. The human cost was staggering. Tank crews who survived one burning tank often refused to get into another. The psychological trauma of knowing that a single penetrating hit could turn your vehicle into an inferno affected morale across entire armored divisions. The 3rd Armored Division reported loss rates of 580%, meaning they lost nearly 6 tanks for every one they started with, constantly receiving replacements just to maintain combat strength. But American engineers at Aberdeen Proving Ground, working with feedback from the battlefields of North Africa and reports from British tankers, developed a solution so elegantly simple that it seems obvious in hindsight. By surrounding ammunition storage bins with water-filled jackets, they reduced the fire rate from 80% to just 10 to 15%. This innovation would save thousands of lives and fundamentally alter the tactical calculus of tank warfare in the European theater. The M4 Sherman medium tank rolled off American assembly lines beginning in February 1942, a product of Detroit's incredible industrial capacity transformed for war. Designed to replace the awkward M3 Lee medium tank, the Sherman represented everything American military doctrine valued: reliability, ease of production, mechanical simplicity, and overwhelming numbers. The first Shermans entered combat with the British 8th Army at the Second Battle of El Alamein in October 1942, just 8 months after the first production models left the factory. Against the German Panzer III and early Panzer IV models, the Sherman performed admirably. Its 75mm gun could penetrate German armor at normal combat ranges of 800 to 1,000 yards. Its reliability was remarkable compared to German tanks. And crucially, it could be produced in vast quantities. Factories across America were churning out Shermans at a rate that Germany, with its overly complex designs and precision engineering requirements, could never hope to match. But there was a problem, and it became apparent almost immediately in the desert campaigns of North Africa. When a German anti-tank round, whether from an 88mm gun, a Panzer IV 75mm, or even a smaller caliber weapon, penetrated a Sherman's armor, the results were often catastrophic. The tank didn't just get knocked out. It burned. Violently. Immediately. The crew would have mere seconds to escape through the hatches before the interior became an inferno. Those who didn't make it out quickly enough faced an agonizing death. Those who did make it out were often traumatized for life. Tank crews began using dark humor to cope. They called their Shermans Ronsons and spoke grimly of brewing up when a tank caught fire. The problem wasn't the fuel. That's what everyone assumed at first, that the gasoline-powered Sherman was more flammable than diesel-powered tanks. But when U.S. Army researchers conducted systematic tests on knocked-out Shermans in 1942 and early 1943, they discovered something alarming. Tanks without fuel or oil that still contained a full load of ammunition burned in 90% of cases when the fighting compartment was penetrated. The fuel wasn't the primary culprit. It was the ammunition. Each 75mm round contained over 2 kilograms of propellant designed to burn quickly and completely. In early Shermans, this ammunition was stored throughout the fighting compartment. 12 ready rounds sat exposed around the base of the turret basket where the loader could grab them quickly, 8 more rounds in a floor rack, additional rounds in the sponsons, the protruding sections above the tracks, and still more ammunition scattered in various bins throughout the tank. When an armor-piercing round penetrated the tank's hull or turret, it often struck one of these ammunition bins. The impact and heat would ignite the propellant in a single round. That round would then set off the others in a cascading chain reaction. Within seconds, the interior of the tank became an inferno reaching thousands of degrees. The turret, weighing several tons, could be blown completely off the tank by the force of the ammunition detonation. The statistics were brutal. British and American after-action reports from North Africa documented Sherman after Sherman burning on the battlefield. Tank crews who survived began exhibiting signs of severe psychological stress. Some refused to enter replacement tanks. Others would deliberately position their tanks behind destroyed vehicles for protection, becoming essentially useless to their units. By mid-1943, the U.S. Army Ordnance Department faced an urgent crisis. They had a tank that worked well in most respects, reliable, mobile, easy to maintain, and available in huge numbers. But that tank was killing its own crews at an unacceptable rate. Something had to change, and it had to change quickly. Lieutenant Colonel Haynes Dugan served as a G-2 intelligence officer with the 3rd Armored Division during World War II. In the years after the war, he collected letters and testimonies from veterans, building a comprehensive picture of what it was really like to fight in a Sherman tank. One letter, from a veteran named Henry J. Earl, captures the terror with shocking clarity. The hit was low on the side. The interior of the tank was lit by a ball of fire caused by the terrific friction of the penetration. A white-hot 18-pound projectile entered the empty ammunition rack under the floor. The steel walls of the compartment prevented the molten metal from striking the interior of the hull and ricocheting throughout the tank. This saved the crew. Earl was lucky. His Sherman's ammunition rack happened to be empty when the German round struck. Many crews weren't so fortunate. The problem had multiple dimensions, each compounding the others into a seemingly impossible engineering challenge. First, there was the physical layout of ammunition storage in early Shermans. The tank carried between 90 and 104 rounds of 75mm ammunition, depending on the specific model. These rounds had to be stored somewhere inside a vehicle that was already cramped with 5 crew members, an engine, a transmission, radios, machine guns, and all the other equipment necessary for a functioning tank. The original design placed ammunition throughout the vehicle for accessibility. The loader needed quick access to rounds during combat. Speed of fire was considered a critical advantage of the Sherman. So 12 rounds sat right at the base of the turret, easily reached. 8 more were in a ready rack at the loader's feet. Still more filled the sponson boxes on each side of the hull, positioned above the tracks where there was available space but also where they were vulnerable to side hits. This distributed storage made tactical sense for rate of fire, but it was a death trap when the tank was hit. Second, the propellant in each round was specifically designed to burn rapidly and completely. This was necessary for proper ballistic performance. The round needed consistent, high-velocity launch characteristics. But that same property made it exceptionally dangerous inside a confined space. Once ignited, the propellant would burn so hot and fast that CO2 fire extinguishers, standard equipment in every Sherman, proved essentially useless. Crews reported triggering the automatic and manual fire suppression systems only to watch helplessly as flames continued to rage. Third, German anti-tank weapons were getting better. The early campaigns in North Africa had featured German tanks and anti-tank guns that were roughly comparable to Allied equipment. But by 1943, Germany was fielding the 75mm KWK-42 gun on the Panther tank and the fearsome 88mm KWK-36 on the Tiger I. These guns could penetrate a Sherman's armor from well over 1,000 yards, often before American tanks even knew they were under fire. German gunners learned exactly where to aim. They knew the ammunition was stored in the sponsons. They knew about the ready racks in the turret. Intelligence reports and interrogations of captured crews gave them a detailed understanding of Sherman's vulnerabilities. German training materials explicitly instructed gunners to target these areas. The psychological impact on Allied tank crews cannot be overstated. Belton Cooper, a maintenance officer with the 3rd Armored Division, later wrote in his memoir, Death Traps. During the European campaign, the division had some 648 Sherman tanks completely destroyed in combat, and we had another 700 knocked out, repaired and put back into operation. This was a loss rate of 580%. Think about what that means. For every tank the 3rd Armored Division started with, they lost nearly 6 over the course of the campaign. Crews were constantly being pulled from destroyed tanks, given replacement tanks, and sent back into combat, often to be knocked out again. Tank crews developed grim rituals. Some refused to learn the names of replacement crew members, knowing they might not survive the next engagement. Others became superstitious about specific tanks, believing certain vehicles were lucky while others were cursed. Still others would drink heavily before combat to numb the fear. British engineers attempted field modifications. They welded additional 1-inch armor plates over the sponson ammunition storage areas. These applique armor patches showed up on many tanks from late 1942 onward, but there was doubt about their effectiveness. A 1-inch steel plate wasn't enough to stop an 88mm round, and even if it helped deflect some hits, it added weight and didn't address ammunition stored in other locations. The U.S. Army's Armored Board recognized that partial solutions weren't enough. In early 1943, they ordered a comprehensive investigation. Engineers at Aberdeen Proving Ground in Maryland received 2 Sherman tanks and a supply of ammunition with explicit instructions. Determine exactly why these tanks burn, and find a way to stop it. The clock was ticking. Allied planning for the invasion of Normandy was already underway, scheduled for spring 1944. Thousands of Shermans would be needed for that operation. If each one had a 60 to 80% chance of burning when hit, the human cost would be catastrophic. At Aberdeen Proving Ground, a sprawling U.S. Army testing facility on the Chesapeake Bay in Maryland, engineers began systematic experiments in the spring and summer of 1943. Their mission was clear, but their path to a solution was anything but obvious. The first step was understanding the exact mechanism of ammunition fires. Engineers loaded Sherman hulls with full ammunition complements and then fired various weapons at them: 37mm guns, 75mm guns, even captured German 88mm rounds. High-speed cameras recorded the results. Thermocouples measured temperatures. Blast gauges captured pressure waves. What they discovered was worse than expected. When an armor-piercing round penetrated the hull and struck an ammunition bin, the impact alone was often sufficient to ignite the propellant. The friction and heat from a steel projectile traveling at over 2,500 feet per second slamming into a brass artillery shell created a spark that found the propellant almost instantly. Once a single round ignited, the fire spread to adjacent rounds within seconds. Each burning round raised the temperature inside the tank. The propellant in nearby rounds would reach its ignition temperature and combust, even without direct flame contact. Within 15 to 30 seconds, every round in the tank could be burning or exploding. The obvious solution, armoring the ammunition bins more heavily, had already been tried and found wanting. You couldn't make the bins strong enough to resist penetration without adding so much weight that the tank would become immobile. And even if you could, the rounds still had to be accessible to the loader during combat. Then someone proposed an idea that seemed almost too simple. What if they surrounded the ammunition bins with water? The concept had precedent in industrial fire suppression, but no one had tried it in a combat vehicle. The theory was straightforward. Water has an extremely high specific heat capacity, meaning it absorbs enormous amounts of thermal energy before it vaporizes. If you could get water between the penetrating round and the ammunition, or between one burning round and its neighbors, you might be able to absorb enough heat to prevent the chain reaction. But implementation presented numerous challenges. First, where would the water go? The ammunition bins were scattered throughout the tank. You couldn't just fill the entire hull with water. The crews still needed to operate in there, and water sloshing around would create its own problems. The solution was elegant. Move all the main gun ammunition to a single location in the floor of the hull, directly below the turret basket, and then design new storage bins with double walls. Each artillery round would sit in an inner metal cylinder, and that cylinder would be surrounded by an outer jacket filled with water and glycerin mixture, later replaced with a proprietary substance called ammudamp that was less corrosive. This wet stowage system meant that when a German round penetrated the tank's hull or turret and struck an ammunition bin, it first had to pass through the outer water jacket. The hydraulic shock would rupture the jacket, spilling water directly onto the impact site and the ammunition. Even if the propellant in one round ignited, the water from adjacent jackets would absorb heat and help prevent the fire from spreading. But moving all the ammunition to the floor created new problems. Early Sherman tanks had batteries, generators, and various other equipment stored in the floor space beneath the turret basket. All of that had to be relocated. The batteries moved to the sponsons. The generator was repositioned to the rear of the transmission. The entire interior layout of the tank had to be redesigned. Additionally, removing the distributed ammunition storage meant the loader's job became harder. In early Shermans, he could grab ready rounds from the turret basket without much difficulty. In wet stowage Shermans, he had to open hatches in the turret basket floor, reach down into armored boxes, extract rounds, and pass them up to load the gun, all while the tank was moving and under fire. Tank crews initially hated this change. They complained that it slowed their rate of fire, which had been one of the Sherman's few advantages over German tanks. Field reports from early 1944 documented crews requesting that old-style ready racks be reinstalled in the turret, even though this would increase fire risk. Many experienced loaders felt they could bail out fast enough if the tank started burning, and they preferred the tactical advantage of faster reloading. But the engineers persisted. Tests at Aberdeen proved the concept worked. Out of 14 ammunition cells penetrated by 37mm and 75mm shells, only 2 caught fire. The other 12 remained intact, or at least didn't burn even when damaged. This was a revolutionary improvement. Moreover, the engineers discovered something unexpected. By consolidating ammunition storage in the protected floor area, they could actually increase the total ammunition load. Late-model 75mm wet stowage Shermans carried up to 150 rounds, more than many early dry stowage models. The reduced vulnerable area meant they could pack more ammunition into a smaller, better protected space. The new wet stowage design was finalized in late 1943. Production began phasing in across different Sherman variants starting in early 1944. The M4A1 with the 76mm gun and wet storage entered production in January 1944. The M4A3 with the 75mm gun and wet storage followed in February. By midsummer 1944, as Allied forces pushed inland from the Normandy beaches, wet stowage Shermans were arriving in increasing numbers. The physical modification was just one part of the solution. The complete redesign required changing hull configurations as well. The switch from small hatch to large hatch hulls coincided with the wet storage implementation. These larger hatches made it easier for crews to escape quickly if something did go wrong, another critical safety improvement that addressed crew concerns. The Army also conducted extensive training for crews transitioning to wet stowage tanks. Loaders had to learn new procedures for accessing ammunition. Commanders had to understand that while their rate of fire might be slightly slower, their survival rate would be dramatically higher. Maintenance personnel learned how to check, drain, and refill the water-glycerin mixture in the storage bins, though in practice, this rarely needed to be done. By August 1944, the majority of replacement Shermans reaching the European theater of operations featured wet ammunition storage. The M4A3, 75W and M4A3, 76W variants, along with the heavily armored M4A3E2 jumbo assault tank, all incorporated the new system as standard equipment. But the question remained, would it work under actual combat conditions? Aberdeen Proving Ground tests were one thing. Facing an 88mm round from a German Tiger tank in the Bocage country of France was quite another. The answer would come from the battlefields of northwest Europe, where German tank crews were about to encounter something they couldn't explain, Shermans that refused to die. The first wet stowage Shermans reached American armored units in the European theater in July 1944, just weeks after the D-Day landings. The 2nd and 3rd Armored Divisions received M4A1, 76W models, the designation W indicating wet storage, and immediately sent them into combat in the desperate fighting around St. Lo and through the hedgerows of Normandy. German after-action reports from August and September 1944 begin documenting a puzzling phenomenon. Tank commanders reported achieving penetrating hits on Sherman tanks at ranges where previous experience indicated the target should have burned. But increasingly, the Shermans weren't burning. They'd be knocked out, tracks blown off, guns disabled, crews bailing out, but they weren't erupting into the characteristic flames that German gunners had come to expect. Intelligence officers interrogating captured American tank crews began hearing about the new ammunition storage system. One German officer's report, captured later in the war, noted with frustration, "The American tanks demonstrate improved fire resistance. Previous targeting doctrine for ammunition storage areas appears less effective. Crews are surviving penetrating hits with greater frequency." The statistical evidence told the story with brutal clarity. A U.S. Army study completed in 1945 analyzed 883 tanks from 1st Army examined between 1944 and 1945. Among wet stowage Shermans that suffered armor penetration, only 10 to 15% burned. Among dry stowage Shermans, the figure remained at 60 to 80%. Consider what this meant in human terms. In a tank unit with 50 Shermans, if 25 of them took penetrating hits during a major engagement, not unusual in the intense fighting of 1944 to 45, the difference was stark. With dry storage, 15 to 20 tanks would burn, likely killing or severely injuring most of the crew members who didn't escape immediately. Approximately 75 to 100 casualties out of 125 total crewmen. With wet storage, only 2 to 4 tanks would burn, reducing casualties to perhaps 10 to 20 men out of the same 125. The same study noted that British and Canadian forces, who largely continued using older Sherman models without wet storage throughout 1944, experienced burn rates above 80%. American units fighting in Italy with older tanks also saw similar high burn rates. The wet storage system wasn't just incrementally better, it was transforming survivability. Tank crews noticed immediately. Staff Sergeant Anthony Hufnagel, 3rd Armored Division, described the difference in post-war interviews. "We got hit 3 times in one day near Stahlberg. First 2 times, we could patch up and keep going. Third time took out the track, but no fire. In my old tank, first hit probably would have been it. We were brewing up left and right in the old ones." The psychological impact was profound. Crews in wet stowage tanks fought with noticeably greater confidence. They were more willing to press attacks, more willing to expose their vehicles to hostile fire when necessary, because they knew that a penetrating hit wasn't an automatic death sentence. Recovery and maintenance units saw dramatic changes in their workflow. Previously, a significant percentage of knocked-out Shermans were total losses, burned so badly that they couldn't be salvaged for anything but scrap metal. With wet storage, many more knocked-out tanks could be recovered, repaired, and returned to service. A Sherman might lose its track to an 88mm hit, be towed back to a maintenance area, receive a new track and some hull patches, and return to combat within days. This had significant strategic implications. The U.S. Army's logistical advantage wasn't just in producing new tanks, it was in keeping damaged tanks fighting. The Germans, increasingly short on raw materials and manufacturing capacity by late 1944, couldn't afford to lose tanks to fire damage that might otherwise have been reparable. The Allies could produce more tanks, and they could keep more damaged tanks in service. Wet storage amplified an existing advantage. German tank crews, meanwhile, struggled to adapt their tactics. Their training and experience had taught them exactly where to aim at a Sherman to guarantee a fire. The sponsons, the ready racks, the ammunition bins, these were known weak points. But wet stowage Shermans had eliminated those vulnerabilities by consolidating and protecting the ammunition storage. German gunnery manuals from 1943 explicitly instructed crews, against the American M4, target the side sponsons and turret ring area where ammunition is stored. Fire is the primary kill mechanism. By late 1944, those instructions were becoming obsolete, but German training couldn't keep pace with the changes. Some German units, particularly those equipped with captured Shermans, the Germans eagerly used any functional enemy tanks they captured, began to appreciate the American vehicle's reliability and now its improved survivability. Photos from late 1944 show German crews with captured wet stowage Shermans, looking notably pleased with their acquisitions. One German tank recovery unit in Italy reportedly preferred using captured Shermans over their own vehicles because of superior mechanical reliability. The Soviet Union also received thousands of Sherman tanks under Lend-Lease, including wet stowage models starting in late 1944. Soviet tanker Dmitry Loza, who commanded a Sherman-equipped unit, later praised the tank's survivability. The Sherman was considerably less prone to catch fire than our T-34 when the ammunition was hit. This gave the crew precious extra seconds to evacuate. But perhaps the most telling evidence of wet storage's impact came from crew casualty statistics. Tank crews in wet stowage Shermans had measurably lower death and severe injury rates than crews in other tanks, even accounting for all causes of casualties, not just fires. This was partly because wet storage worked, and partly because crews who weren't terrified of burning were more effective in combat. A confident crew fought better, made better tactical decisions, and was more likely to survive. By the Battle of the Bulge in December 1944, Germany's last major offensive in the West, the majority of American Sherman tanks in a European theater featured wet ammunition storage. When the 2nd SS Panzer Division used captured Shermans, including at least one wet stowage model, to infiltrate American lines at Mannheim on Christmas Eve 1944, it spoke to both German desperation and grudging respect for the vehicle's capabilities. Through the final campaigns of the war, the push across the Rhine, the reduction of the Ruhr pocket, the drive into southern Germany, wet stowage Shermans proved their worth repeatedly. They weren't invulnerable. German 88mm guns could still knock them out. Panzerfaust rocket launchers could still destroy them at close range. But they had gone from being mobile crematoriums to survivable combat vehicles. Post-war analysis confirmed what frontline troops already knew. The wet ammunition storage system had saved thousands of Allied lives and kept thousands of tanks in the fight that otherwise would have been lost. It represented exactly the kind of practical, implementable solution that characterized the best of American engineering. Not perfect, not revolutionary, but effective and achievable at scale. The Sherman tank's wet ammunition storage system represents far more than a simple modification to improve one tank's survivability. It stands as a case study in responsive engineering, institutional learning, and the crucial connection between frontline experience and design innovation during wartime. In the broader context of World War II tank development, the wet storage solution revealed something important about different national approaches to weapons design. German tanks by 1943-44 were often superior on a one-to-one basis. The Panther had better armor and a more powerful gun, the Tiger was nearly invulnerable from the front, and both could outrange the Sherman. But German tanks were mechanically complex, difficult to produce, expensive to maintain, and, crucially, when they were destroyed, they stayed destroyed. The American approach prioritized different values. Make them reliable. Make them simple. Make lots of them. And critically, make them survivable. Wet storage perfectly embodied this philosophy. It didn't make the Sherman better at killing enemy tanks. It made American tank crews better at surviving combat. That distinction mattered enormously in a war of attrition. Consider the mathematical reality. Germany produced approximately 6,000 Panther tanks and 1,800 Tigers during the entire war. The United States produced over 49,000 Shermans. Even if a Sherman only had a 1 in 5 chance of surviving an encounter with a Panther, the Allies could afford to send 5 Shermans for every German tank. But with wet storage improving survival rates, those odds shifted further in Allied favor. A wet stowage Sherman had perhaps a 1 in 3 chance instead of 1 in 5. Suddenly, the numbers game became overwhelming. The innovation also demonstrated the importance of systematic testing and scientific methodology even under wartime pressure. The engineers at Aberdeen Proving Ground didn't just try random solutions and hope something worked. They conducted controlled experiments, measured results, analyzed failure mechanisms, and designed a solution based on evidence. This methodical approach took time, roughly 18 months from initial investigation to production implementation, but it produced a solution that actually worked rather than a hasty field modification that might have been ineffective. The institutional responsiveness is equally noteworthy. The U.S. Army's Ordnance Department, Armored Board, and theater commanders created feedback loops that brought information from the battlefield back to engineers who could act on it. British reports from North Africa in late 1942 documenting Sherman fire vulnerability reached Aberdeen Proving Ground within weeks. By early 1943, systematic testing was underway. By late 1943, production plans were being modified. By mid-1944, improved tanks were reaching combat units. For a military bureaucracy managing a global war, this represents remarkable agility. Compare this to German tank development during the same period. When German crews reported problems with the Panther's final drive breaking down, or the Tiger's transmission failing, these reports went up the chain of command, but solutions were slow to materialize. German industry, operating under constant air attack and facing raw material shortages, couldn't easily implement modifications. The complex engineering that made German tanks formidable also made them difficult to improve iteratively. The human element of this story deserves emphasis. Behind every engineering decision were men, and a few women, making choices that would determine whether thousands of young soldiers lived or died. The engineers at Aberdeen Proving Ground understood that their work wasn't abstract. Every day of delay meant more tank crews burning to death in the fields of France or the deserts of North Africa. This awareness drove them to work with urgency but also with care, because a flawed solution could be worse than no solution. Tank crews themselves played a crucial role. The reports, complaints, and suggestions from frontline soldiers provided essential data. When crews reported that ammunition stored in sponsons always seemed to ignite, or that certain hit locations consistently produced fires, this information guided engineering efforts. The Army, to its credit, listened to these reports and acted on them. The legacy of wet ammunition storage extends beyond World War II. Post-war tank designs, both American and international, incorporated similar protective measures. The M26 Pershing heavy tank, which arrived too late to see significant World War II combat, featured wet storage from the outset. The M46, M47, M48, and eventually the M60 series all used variations on the concept. Modern armored vehicles use even more sophisticated systems: blowout panels that channel ammunition explosions away from the crew, fire suppression systems that deploy in milliseconds, and separated ammunition compartments, but they all descend from the principles established with Sherman wet storage. The broader lesson applies to any field facing life-and-death challenges. Identify the real problem, apply systematic analysis, implement solutions based on evidence, and maintain feedback loops between users and designers. This sounds obvious, but it's remarkably difficult to execute in practice, especially under wartime pressure when institutional inertia, budget constraints, and political considerations often interfere. Some critics argue that wet storage was too little, too late, that the U.S. should have developed a heavier tank with better armor and firepower rather than trying to make the Sherman survivable. This criticism misses the point. The Sherman, with all its limitations, was available in huge numbers by 1943. A hypothetical better tank that existed only on drawing boards wouldn't save any lives. The wet storage solution made the tanks that were actually fighting, and would continue fighting for the rest of the war, dramatically more survivable. Moreover, the wet storage modifications didn't prevent development of better tanks. The M26 Pershing heavy tank was under development throughout this period. But Pershing production ramped up slowly, with only 2,000 units produced before war's end, most too late for combat. The Allies won the war with Shermans, and wet storage helped ensure that the men who fought in those Shermans had a fighting chance of survival. The story also illuminates broader truths about innovation under crisis. The best solutions are often not the most elegant or sophisticated. They're the ones that can be implemented quickly, at scale, with existing manufacturing infrastructure. Wet storage required redesigning the hull interior and manufacturing new ammunition bins, but it didn't require new steel alloys, advanced metallurgy, or exotic materials. It used water, perhaps the most abundant substance on Earth, combined with clever engineering. This pragmatic approach to innovation contrasts sharply with technological perfectionism. German weapons development in World War II often pursued theoretical excellence over practical effectiveness. The result was weapons like the Tiger II heavy tank, extraordinarily powerful but so mechanically complex that many broke down before reaching combat. The Americans pursued good enough right now in large quantities. In a war of attrition, this philosophy proved superior. For modern viewers watching this story unfold, the lessons remain relevant. Whether in military technology, civilian infrastructure, public health, or any field where lives depend on good design, the principles hold. Listen to users, test systematically, implement solutions that work rather than solutions that are perfect, and maintain institutional mechanisms that allow for rapid improvement. The men who fought in Sherman tanks with wet ammunition storage didn't know they were participating in a remarkable engineering success story. They just knew that when their tank got hit, they had a much better chance of walking away. That's what matters. Engineering serves humanity, and the best engineering saves lives. So the next time you see a Sherman tank in a museum, or preserved as a monument outside a VFW hall, remember that behind its simple, boxy silhouette lies one of the great problem-solving efforts of the 20th century. Remember the engineers at Aberdeen Proving Ground who worked around the clock to find a solution. Remember the tank crews who sent back reports documenting the problem. Remember the production workers who retooled assembly lines to implement the fix. Remember the thousands of young men who climbed into these tanks knowing they might burn, and who fought anyway. Before you go, hit that like button if you learned something today. Subscribe to the channel for more deep dives into the engineering and human stories behind military history. And leave a comment. I want to hear from you. Did you know about wet ammunition storage before watching this? Do you have family members who fought in Shermans? Have you visited a tank museum and seen these machines up close? This is the kind of story that deserves to be remembered. Because innovation doesn't always come from brilliant flashes of insight. Sometimes it comes from methodical work, institutional responsiveness, and engineers who understand that their drawings and calculations represent human lives. The Sherman's wet storage system saved thousands of those lives. And that's a legacy worth celebrating. Thanks for watching. See you in the next video.